color strings, so we expand once more. Now, something interesting has happened because we find an LCP value of 3, which is larger than our current best value. So we update the solution set to have the string BCD instead of just BC, which is 1 character longer. Now we get to shrink the window size. The window is now too small, so we expand the LCP value of 0 here, so that is no good. So shrink the window size. Now expand to meet the color requirement. We get an LCP value of 1, but that doesn't beat our current best, which is 3. So shrink the window. Now we need to meet the color requirement, so expand. We have only blue strings, so keep expanding. An LCP value of 1 for this window range. So that's no good. So shrink. Now we have an LCP value of 2. We're getting closer to our best, but still not good enough. So we have to shrink and let it go. Now expand. Now something interesting is going on here. We have a window LCP value of 3, which is equal to our best so far. So instead of saying that CDE, our newfound longest common substring value, beats BCD, which is of the same length, we keep both in the solution set. Alright, so now let's shrink our window interval because we meet the color requirement. Now expand it. We still need one more color. Expand again. Our LCP window value is 0. So shrink and shrink again. Now expand. LCP value of 1 here. That's not good enough. So smaller. Expand. LCP value of 2. Okay, we might be getting closer, but we meet the color requirement, so shrink. Now expand to meet the color requirement. These two strings have an LCP value of 0. So shrink. Now expand. Now shrink. Now we've reached the end and found our solution to the longest common substring problem with 4 strings and a k value of 2. As I was doing the window expanding and shrinking, I wanted you to notice that each time the window either expanded or shrank, I only ever moved one of the endpoints downwards, and they were always going downwards. So we know that the number of windows has to be linear in proportion to the number of suffixes that we have. And the number of suffixes that we have is the length of our text, t. So we come to the conclusion that there must be a linear amount of windows that we must consider, which is really good because we want our time complexity be quick. Today's topic is going to be on an efficient way to solve the longest repeated substring problem. The longest repeated substring problem is another one of these fairly common problems in computer science. Lots of problems can actually be reduced to this problem, so it's important that we have an efficient way of solving it. The naive approach requires n-squared time and lots of space. What we want to do instead is use the information stored inside the longest common prefix array to yield a faster and also space-efficient solution. Let's do an example. What is the longest repeated substring of the string abracadabra? Feel free to pause the video and figure it out yourself. The answer is the substring abra, which is the longest substring that appears at least twice in the string. So we call it the longest repeated substring. Here you can see the first instance of abra on the left. And now you can see the second repeated instance of abra on the right. Although these substrings are disjoint and do not overlap, in general, This is permitted for the longest repeated substring. Now, let's solve the problem using a suffix array and an LCP array, which I have generated on the right-hand side. I'll give you a moment to pause the video and inspect the LCP array in case you notice anything special in relation to the longest repeated substring, now that you already know what the answer is. Effectively, what we're looking for in the LCP array is the maximum value. Intuitively, we want to do this because we know that the suffixes are already sorted. So if two adjacent suffixes have a large longest common prefix value, then they share a good amount of characters with each other. We also know that if the LCP value at a certain index is greater than 0, then the string shared between the two adjacent suffixes is guaranteed to be repeated because it is common between two suffixes, each of which start at different locations in the string. So here again is abracadabra. Since our LCP value was 4, we know that the first 4 characters from the suffix abracadabra forms one part of the repeated substring. Next, we know that the suffix above it, which shares the LCP value of 4, also shares 4 characters present in that longest repeated substring. Now, I want to look at another interesting case. Can you find the longest repeated substring of the string A, B, A, B, B, A, A, B, A, A? Well, if you did, you would find out that you not only got one longest repeated substring, but 2 longest repeated substrings, since there can be ties. In a case like this, you're not looking for a single largest value, but all largest values that might exist. For the first maximum, you can see that we'll want the first 3 characters from the suffix A, B, A, B, B, A, B, A. And for the second maximum, we'll want the first 3 characters from the suffix BAA, BAA. Visually, for this first longest repeated substring, we have ABA, which appears at the start, and then ABA again closer to the end. The other repeated substring is found using the second largest common prefix value, and its first occurrence is found here, and the second one just next to it. That is all for repeated substrings. Pretty easy once the suffix array and the LCP array have already been constructed. Here is a practice problem on Caddis if you want to tackle a longest repeated substring problem which requires you to have an efficient solution. Today I'm going to introduce probably one of the most important types of trees in computer science, which are balanced binary search trees. Balanced binary search trees are very different from the traditional binary search tree because they not only conform to the binary search tree invariant, but they are also balanced. What I mean by balanced is that they are self-adjusting to maintain a logarithmic height in proportion to the number of nodes they hold. This is very important because it keeps operations such as insertion and deletion extremely fast because the tree is much more squashed. In terms of complexity, a binary search tree has average logarithmic operations, which is quite good. However, the worst case still remains linear because the tree could degrade into a chain for some inputs. One such input is a sequence of increasing numbers. To avoid this linear complexity, we've invented balanced binary search trees in which the worst case is logarithmic for all operations, which makes them very appealing. Central to how nearly all balanced binary search tree implementations keep themselves balanced is the concept of tree rotations, which is going to be the main topic of this video. Later, we'll actually look at some specific types of balanced binary search trees to see how these rotations come into play. So, the secret ingredient to most balanced binary search tree implementations is the combination of 2 things. 1. A clever tree invariant, and tree rotations. A tree invariant is simply a property or a rule that you impose on your tree, such that it must be met at the end of every operation. To ensure that the invariant is always satisfied, a series of tree rotations are normally applied. We'll get back to this concept of invariants in a later video, so don't worry about them so much for now. Right now we're going to look at how tree rotations work. Suppose our invariant is not satisfied, and to fix it, we need to do a right rotation about node A. Assuming node A has a left child B, we can perform a right rotation to put B where node A was and push node A down to become B's right child. When I first learned about this in my undergrad, I was mind blown, literally. I thought it was absurd, or even to the point of being illegal, that we should be allowed to do this and just move around nodes in a tree. But what I've realized since is that a transformation like this is totally legitimate, since we're not breaking the binary search tree invariant in any way. If you inspect the left tree, you'll discover that in terms of ordering and placement, node D is less than node B is less than E is less than A is less than C. Then you inspect the right tree and remark that, well, this is also true. A bit more detail on why performing tree rotations is a valid operation. First, you have to remember that all balanced binary search trees are binary search trees, meaning that the binary search tree invariant holds. So for every node n, the values in the left subtree are less than the value of n, and the values in the right subtree are all greater than the value of n. So in this sense, it doesn't matter what the tree structure itself looks like. All that fundamentally matters is that the binary search tree invariant holds. This means we are free to shuffle, transform, or even rotate the values of the nodes in our tree as we please, as long as the binary search tree invariant remains satisfied. Now let's look at how these rotations are done in great detail. For simplicity, since the rotations are symmetric, I will only do the right rotation, and you should be able to figure out the left rotation on your own. First, have a look at the tree on the right. Notice that there are directed edges pointing downwards, and another node P above A, which may or may not exist. This is why there is a dotted line on that edge. If node A does have a parent node P, then it is important that we take it into account when doing the rotation. In either case, we start with a pointer reference to node A. This is the orange arrow. Then we'll want a pointer to node B. After that, set A's left pointer to point to B's right child. Then change B's right pointer to point to node A, and we've successfully done a right rotation. If we rearrange the nodes, this is what we would end up with. However, notice that there's a slight problem. If node A had a parent node, then either the parent's left or right pointer would still be referencing A. This is problematic since B is A's successor after the rotation. So we change the link to now point to B. This step is usually done on the recursive callback using the return value of the right rotate function. We just finished looking at the case where each node has a reference to the left and the right child nodes. But in some balanced binary search tree implementations, it's more convenient for nodes to also have a reference to the parent node. This complicates tree rotations because now, instead of updating 3 pointers, we need to update 6 pointers. Let's have a look. In this case, where we also have a parent link, every node is, in a sense, doubly linked. We start off with a pointer referencing A, and the first thing we'll want to do is also reference node B and node P, so we don't lose them as we shuffle around pointers. Next, we'll adjust the left subtree of A to make A's left pointer reference B's right subtree. Of course, throughout this example, assume B is not null. If you're paranoid, you can add an extra if statement to check for this condition. However, it would be a mistake to assume B's right subtree is not null. We actually have to check against this before setting B's right child's parent to reference A. Next, let's make A the right subtree of B, so set B's right pointer to reference A. Now make A's parent pointer reference B. The last thing we need to do is adjust the reference to the parent node P, so make B's parent pointer reference P. And now the very last thing I promise is to make P's left or right pointer reference the successor node B. Notice that we need to check if P is not null because it might not exist. This would be the case for the root node. If we readjust the tree, you will see that we correctly did a right rotation. There are a lot of steps in doing this right rotation, and it's a very error-prone process, which is why I wanted to do it in such detail. Today we're going to look at how to insert nodes into an AVL tree in great detail. We'll be making use of the tree rotation technique we looked at in the last video, so if you didn't watch that, simply roll back one video. Alright, before we get too far, I should mention what an AVL tree is. An AVL tree is one of many types of balanced binary search trees, which allow for logarithmic insertion, deletion, and search operations. Something really special about the AVL tree is that it was the first type of balanced binary search tree to be discovered. Then, soon after, a whole bunch of other types of balanced binary search trees started to emerge, including the 2-3 tree, the AA tree, the scapegoat tree, and the AVL tree's main rival, the red-black tree. What you need to know about next is the property that keeps the AVL tree balanced, and this is the balance factor. Simply put, the balance factor of a node is the difference between the height of the right subtree and the left subtree. I'm pretty sure the balance factor can also be defined as the left subtree height minus the right subtree height, but don't quote me on this. It would also screw up a lot of what I'm about to say, and may also be the reason why you find many inconsistent ideas about what way to do tree rotations on various Google search results pages. So for consistency, let's keep the balance factor right subtree height minus left subtree height. For clarity, because people get this wrong or define it differently, the height of node X is calculated as the number of edges between X and the furthest leaf. So if your tree only has one node, the tree has height 0, not height 1, because there are no edges. The invariant on the AVL tree that keeps it balanced is forcing the balance factor of every node to be either -1, 0, or +1. If the balance factor of a node is anything else, we need to resolve that with tree rotations. In terms of information we need to store in each node to actually make the AVL tree work, what we'll need is the actual value the node stores. This value must be comparable so we know how to insert it and in what position it goes in the tree. Then we'll also need the balance factor and height of the node as well as the left and the right child pointers. As the algorithm executes, we'll need to update these values, so keep that in mind. So a slide or so back, I said that the balance factor of a node must always be -1, 0, or +1. A natural question to ask is, how do we handle the case where this is not true? The answer is that if this is not true, then the balance factor must either be +2 or -2, which we can easily handle with tree rotations. The rotations we need to perform, depending on the structure of the tree, can be broken down into 4 distinct cases. The first such case is when the tree is what we call a left heavy, and there are 2 left child nodes. This is an easy case to fix because all we need to do is perform a right rotation about the yellow node to balance. The next case is the left-right case, where you have a left child, but then that node has a right child. To fix this, you do a left rotation about the left child, so the green one on the leftmost image. What happens then is that this transforms into the left-left case we just saw, which we can resolve with a right rotation to balance. The third case is the right-right case, which is symmetric to the left-left case. So instead of doing a right rotation, we do a left rotation about the green node. Last but not least is the right-left case, which is symmetric to the left-right case. For this case, you would perform a right rotation about the yellow node on the leftmost image to transform this case into the right-right case, and then do a left rotation about the green node in the middle image. Next, I want to show you some pseudocode for inserting nodes into an AVL tree because it's not all that obvious or easy. This first method is the public-facing method for the insert method, which returns true or false depending on whether the value was successfully inserted or not. For simplicity, we're going to ban duplicate values in our AVL tree. So if the value already exists or the value is null, this method would return false. If the node is not null and it doesn't already exist in the tree, we call our private recursive insert method, where we pass in a pointer to the root node and the value we want to insert. The private recursive method is also simple. If we hit the base case, a null node, we simply return a new instance of the node with the value we want to insert. Otherwise, we get the comparator value with the value we're trying to insert against the current node to determine if we should go on the left or the right subtree. After that, on the recursive callback, we call the update method, which updates the balance factor and height values for this node. And lastly, we rebalance the tree with the balance method. Now, let's take a look at the update and balance method and what they're actually doing. The update method updates the balance factor and height values of our node. So to calculate the height of the node, we get the maximum height of the left and the right subtrees and then add 1. Notice that I initialize the left and the right subtree heights to be -1. This is because it will cancel out with a +1 with the max function in the case where the node has no subtrees, giving the correct height of 0 for leaf nodes. Lastly, I update the balance factor for this node by finding the difference between the right subtree and the left subtree heights. The balance method is slightly more involved, but not too crazy. Here we check if our balance factor has an illegal value of -2 or +2. If the balance factor is -2, then we know that the node is left heavy. Then we dig further into the left subtree to determine if we're dealing with a left-left case or a left-right case. We do a similar thing if the balance factor is +2, except we're dealing with the right-right or the right-left case. If the balance factor is not +2 or -2, then we know that the balance factor is going to be either +1, 0, or -1, and in either of those cases, we don't need to do anything. Inside the 4 cases we might run into, notice that all we do here are calls to the left rotation and right rotation methods that we saw in the last video. Also notice that the left-right and right-left cases call the left-left and write case methods respectively, since they reduce to those cases after a first rotation. In the last video, we looked at this write rotation method, but since we're dealing with an AVL tree in this video, we actually need to augment that method to update the height and balance factor values for the nodes we're moving around when we do rotations. This is a subtle detail you must not forget, otherwise your height and balance factor values will be inconsistent. The left rotation case is symmetric to this one, so you should be able to figure it out pretty easily. In this video, we're going to look at how to remove elements from an AVL tree. And what you'll discover is that removing elements from an AVL tree is almost identical to removing elements from a regular binary search tree. So for the majority of this video, we're going to actually be looking at how to remove elements from a binary search tree, and at the very end, augment that algorithm for AVL trees specifically. So let's get started. So just for review, I want to look at how to remove nodes in a binary search tree in detail. So we can generally break it up into two steps: finding and replacing. In the find phase, you find the element you want to remove from the tree, if it exists, and then replace it with a successor node. The successor node is necessary for us to maintain the binary search tree invariant. More details on the find phase. This is when we're searching for the element in the tree to see if it exists, and basically, four things can happen. First is we hit a null node, in which case we know that the value we're looking for doesn't exist. Our comparator returns a value of 0, meaning we found the node we want to remove. The comparator value is less than 0, so the value we're looking for, if it exists, is going to be found in the left subtree, or the comparator value is greater than 0, in which case the value, if it exists, is in the right subtree. So let's do an example of finding nodes in a binary search tree. Suppose we're looking for 14. Well, we should have a reference to the root node, so this is where we start. So we compare 20 and 14, and we know 14 is less than 20, so we go on the left subtree. We know 14 is greater than 10, so we go on the right subtree. We know 14 is less than 15, so we go in the left subtree. 14 is greater than 12, so the right subtree. And finally there, we found it, the node we were looking for. Now let's see what happens with a node that doesn't exist. So let's try and find 26. So again, we start at the root node, then we go to the right subtree because 26 is greater than 20. Then we go to the left subtree because 26 is less than 31. Then once we're at 25, we would go to the right subtree and then discover that 26 does not exist in the tree. So once we find the node, assuming it exists, we need to replace that node with its successor. The motivation for this is that if we just remove the node without finding a successor, then there'd be a gap in the tree. And when we're looking for a successor node, one of four cases will happen. Either we're a leaf node, in which case there are no subtrees. The node to remove has no left subtree, the node to remove has no right subtree, or the node to remove has both a left subtree and a right subtree. We'll see how to handle all these cases. In the first case, where the node to remove is a leaf node, we can simply remove it without any side effects. The successor node in this case would be simply a null node. So suppose we want to remove node 8 from this tree. The first thing we do is find out where 8 is in the tree. So we'd go down the tree and then we'd found node 8. Then we discover that, oh, it's a leaf node, so we can just remove it, like so. Alright, now for cases 2 and 3, where there's only a left or a right subtree, in these cases, the successor node is the immediate child of that left or right subtree. The reason the successor is the immediate node down from the node we're removing is that it is the next node which is either greater than it in the case of a right subtree, or less than it in the case of a left subtree. Let's do an example. Suppose we want to remove node 9. The first thing we do is find where node 9 is in the tree. So start at the root and go to the right subtree and then find the node we want to remove, which is 9. And then we inspect 9 and discover that it only has a left subtree. So the successor node is its immediate child on the left, so 7. So what we do is we get a reference to 7 and then get ready to remove 9. And then we remove 9 and then make 7 the successor by linking it back up to 5. And if we rebalance the tree, that's what it looks like. And node 9 has been removed. So the last case is when the node we're trying to remove has both a left subtree and a right subtree. So the question in this case is, in which subtree will we find the successor of the node we're trying to remove? And surprisingly, or not surprisingly, the answer is both. The successor can either be the largest value in the left subtree or the smallest value in the right subtree. Once the successor node has been found in either that left or right subtree, we replace the value of the node to remove with a value in the successor node. However, the story doesn't end there. We must not forget to remove the duplicate value of the successor node that still exists in the tree. One common strategy to resolve this is to recursively call the function again, but with the value to remove as the value in the successor node. Let's see an example because this isn't completely trivial. Let's remove node 7 from this tree, which is the root node. So we would start at the root node and discover that in fact, this is the node we want to remove, and notice that it has 2 non-empty subtrees, so we must choose a successor. To choose a successor, we either pick the smallest value in the right subtree or the largest value in the left subtree. Let's find the smallest value in the right subtree. And to do this, you would go to the right once and then dig as far left as possible. So now that we found the successor node 11, we would copy its value into the node we're trying to remove, which is the root node 7. Notice that now there are 2 instances of 11 in our tree, and we want unique values in our tree. So to remove the 11 that is currently highlighted, we would recursively call our remove method, but on 11 this time. And luckily for us, this will always result in a case 1, 2, or 3 removal. So to remove 11, we notice that it only has a right subtree, so its successor is its immediate right child. So we stage the removal and get ready to remove 11. Then we remove 11 and then hook 14 back up to 18. And if we rebalance the tree, then we can see that the duplicate 11 value is gone. Alright, the moment we've been waiting for. How do we augment the binary search tree removal algorithm for AVL trees? The solution is simple. You only need to add 2 lines of code to ensure that the tree remains balanced and that the balance factor and height values remain up to date. On the recursive callback, you invoke the update and balance methods you saw in the insert video, which ensure that when the node is removed from the AVL tree, that the tree remains balanced. It's as easy as that. Today we're going to have a look at some of the source code for the AVL tree. The link to the source code I'm going to present in this video can be found on GitHub at github.com/WilliamFiset/data-structures. Make sure you have watched the last 3 videos on the AVL tree about tree rotations, insertions, and removals in AVL trees before continuing so you can understand the source code I'm presenting. I don't normally do this, but I'm going to present a live demo of the AVL tree in action. So I'm here in my GitHub repository. I'm just compiling some of the Java code for the AVL tree, and then I'm going to run it. and you see that it generated a random tree with some values. And notice that the tree is relatively well balanced for the number of nodes that are in it. So I randomly inserted some nodes, and you might expect the tree to be a bit more sloppy if it were just a simple binary search tree, but the AVL tree really keeps the tree quite rigid. So I think we're ready to dive into the source code now. Here we are in the source code of a recursive AVL tree implementation in the Java programming language. So let's get started. If you look at the class definition for the AVL tree, you'll notice that this class takes a generic type argument, which is of type T, which extends to comparable. And this generic type I'm defining basically says that the types of values we're going to be inserting inside the tree need to be comparable in a sense, meaning we need to be able to insert them and know how to insert them. So if you look inside the subclass node, which I've created, you can see that the value we're actually storing inside the node is of type T, so it's a comparable. And that's very important. The other instance variables I'm storing inside the node subclass for this AVL tree is, of course, the balance factor as an integer, the height of the node, because we want to be able to query the height of a node in constant time, so I'm storing it inside every node. And then, of course, there's going to be the left and the right child pointers right here. And notice that this node class implements the tree printable node interface, and that's just an interface I have somewhere in this folder that allows me to display the tree I did on the terminal. So this isn't quite a requirement if you're actually building an AVL tree, and nor are these overrides. Those are also for being able to display the tree in the terminal, which is really handy for debugging actually. All right, so instance variables at the AVL tree class level, we have the root node. This should really be private, although I'm using it for testing, so I'm leaving it packaged private. I'm also keeping track of the number of nodes inside the tree, inside this node count variable. Something else I'm also using for testing is this height function, although it's really good to just sanity check yourself to make sure that your AVL tree height is relatively low. Then there are these methods like size and isEmpty, which are pretty self-explanatory. This is the display method I call to actually print the tree in the terminal. This is a contains method to check if a certain value already exists inside the tree. So this is the public-facing method, which calls the private method, and I give it the root as the initial node to start off with. So to check if a node exists inside a tree, if we hit the base case, then we know that that value does not exist. Otherwise, we compare the current value to the value inside the node. So that returns a comparator value of either a value less than 0, which means that if the value does exist, it'll be found in the left subtree, or comparator is greater than 0, meaning the value, if it exists, is in the right subtree. Otherwise, that means that the comparator value is equal to 0, and that means we found the node inside the tree, so we can return true. So we're trying to insert this value variable. If it's null, we don't want anything to do with it, so we just return false. And we return a Boolean for the insert method to indicate whether an insertion was successful or not. So if the value does not already exist inside the tree, then we're going to call the private insert method and then assign its value to the root and also increment the node count, because we know we're going to successfully insert something if we're inside this block. And at the same time, we're going to return true. All right, let's have a look at the private insert method. So if we reach the base case, meaning we traverse all the way down our tree and the value of node is null, then we know this is the position where we need to insert that new node. So create a new node and give it the value. Otherwise, we're searching for the insertion position. So again, invoke the comparator function, then do value.compareTo node.value. This .compareTo comes from the comparable interface at the class level. So that's why we're allowed to invoke .compareTo on a generic type here and another generic type there. So again, if comparator is less than 0, then insert in the left subtree. Otherwise, insert in the right subtree. And here is the extra 2 lines you need to add for the AVL tree, which is calling the update method to update the balance factor and the height value for this node, and also rebalance the tree if necessary. Well, rebalance the tree at this node. All right, so let's look at the update method. So this is to update the balance factor and height of a node. So here are 2 variables that grab the height of the left subtree and the right subtree. Then I update the height for this node. So that's always 1 plus the maximum of either the left subtree or the right subtree height. Then once we have the appropriate values for left and right, we can, of course, update the balance factor, which is the difference between the right and the left subtree heights. Okay, so we've done the update. Now we can call the balance method. And inside the balance method, we're looking to readjust nodes whose balance factors are either -2 or +2. In the case of a -2, this means that our tree is left heavy. And inside the left heavy case, we can run into the left case or the left right case. And inside the right heavy case, we have the right case and the right left case. And to identify those subcases, you just check the balance factor, but on either node.left or node.right, respectively. And if the balance factor of the node is not -2 or +2, then we know that the balance factor is either 0, +1, or -1, which is fine, and we don't have to touch anything. We don't have to rebalance the tree if either one of these is true. So we just simply return the node. So now we can look at the individual cases themselves. So like the left case will just perform a right rotation. The left right case will do an initial left rotation and then call the left case. So we're reusing methods we already wrote here, since this case degrades to that case after one rotation. And a similar thing happens for the right case and the right left case. We get to call the right case after one right rotation over here. Then here are the notorious left rotation and right rotation methods. For the AVL tree, it's very important that we call these 2 update methods to update the height and balance factor values after that we've rotated about this node, because those values will undoubtedly change. And it's also important that this is the order you do them in. You can't do them in inverse order because you have to update the child node first to get the correct balance factor and height values for the parent. Okay, now we're at the remove method. So in this remove method, we want to remove this element, or I should have called it value rather, but still. So if the element is null, well, we know it doesn't exist in the tree, so just return false. Otherwise, make sure that value exists in the tree and then remove it by calling the private remove method. Then decrease the node count and simply return true on the remove method to indicate that the removal was successful. So let's look at this private remove method where all the action is happening. So if we hit the base case, just return null, then we get our comparator value, and we do what we always do. We check if the comparator is less than 0, and if so, we dig into the left subtree, and we know that the value we're looking for is smaller than the current value. And then we recursively call the remove method, but passing down node.left. So we're just decreasing the region we're searching, and then pass in the element as well. Otherwise, do the same thing, but for the right. So recurse down the right subtree. Otherwise, if this is not true and that is not true, then we know that the comparator value is equal to 0, meaning we found the node we wanted to remove. And we know from the slides that this is where the 4 cases come up. If node.left is equal to null, then we know that we want to return node.right, or if node.right is null, meaning the right subtree is null, then return node.left. Okay, and then the final tricky case where we're trying to remove a node who still has both subtrees. So the left subtree is there and the right subtree is there, but we still want to remove that node. And we can either pick the smallest value. Well, the successor can either be the smallest value in the right subtree or the largest value in the left subtree. And I'm using a heuristic right here to actually determine which one I want to do, just because I think it's a good heuristic. And here's what it is. If the height of the left subtree is greater, I want to remove nodes from that subtree. But otherwise, if the right subtree has a larger height, then I want to remove nodes from that subtree. So that's the heuristic I'm using to choose which subtree I remove from. And I just made up this heuristic, but I think in general it'll work pretty well. So what we do, let's say there are or the left subtree has a larger height, then what I'm going to do is I'm going to find the successor value by going down the left subtree once and then digging all the way to the right to find the max value, and then swapping that value into the current node. And then this is the recursive part. We recurse on removing the successor value instead of the element we passed in, or rather the element we passed in becomes the successor value. So we've removed the element, but now we also have to remove the successor value because we don't want duplicate values inside our tree. Then we basically do the same thing, but on the other side, if the condition goes the other way. Here's what I was mentioning in the last video, where you want to call the update and rebalance method on the callback of this remove method. so that the tree remains balanced even though we're removing nodes. And these are the find min and find max method I was calling right up here, which just digs left or digs right, depending on the case. And here's just an iterator to traverse the tree. I don't think I need to go over this. And here's another method for testing, which validates the binary search tree invariant, also not particularly important. And this is what I was calling in the main function that will just randomly insert values inside the tree and then display it. So when I invoked this file on the terminal, this is what executed. So that is an AVL tree. It's pretty cool data structure, and I quite enjoyed writing it up. Today's data structure is the indexed priority queue. This is going to prove to be a very useful data structure that you wished you would have known a long time ago. So just before we get started, this video builds off concepts from the previous priority queue videos, which simply go over the basics. Strictly speaking, you can probably get by without watching all those videos, as I'll be doing a quick recap. But for those of you who want to know priority queues in full detail, please check out the description for links to those. So what exactly is an indexed priority queue? Well, it's a traditional priority queue variant which, on top of having all the regular priority queue operations, also supports quick updates and deletions of key value pairs. One of the big problems that the index priority queue solves is being able to quickly look up and dynamically change the values in your priority queue on the fly, which is often very useful. Let's look at an example. Suppose a hospital has a waiting room with n people, which need different levels of attention. Each person in the waiting room has a certain condition that needs to be dealt with. For instance, Mary is in labor, so she has a priority of 9. Akarsh has a paper cut. He has a priority of 1. James has an arrow in his leg. He has a priority of 7. Naida's stomach hurts. She gets a priority of 3. Richard has a fractured wrist, so his priority is 5. And lastly, Leia also has a stomach that hurts. We want to process these patients by highest priority first. This means the hospital would serve Mary first, followed by James. However, then something happens. Suppose Naida's stomach condition worsens and she starts vomiting. Her priority needs to get updated to 6. Because of this, Naida gets served next once they're finished with James. During this time, Richard gets impatient and leaves. He goes to another clinic down the street, so he no longer needs to be accounted for. Further, suppose that Akarsh goes to take a drink of water, slips on the floor, and as a result cracks his head and needs immediate attention, so we increase his priority to 10. Once Naida is dealt with, Akarsh should be next. And lastly, this is followed by Leia. As we saw in the hospital example, it is very important to be able to dynamically update the priority of certain people. The index priority queue is a data structure which lets us do this efficiently. The first step to using an index priority queue is to assign index values to all the keys, thus forming a bidirectional mapping. If we use an index priority queue to track who should get served next in our hospital, we need to assign each person a unique key index value between 0 and n non-inclusive. Note that this mapping is intended to be bidirectional, so I would advise using a bidirectional hash table to be able to flip back and forth between the key and its key index. Basically, any operation on the index priority queue will require the associated key index of a particular key. So you're probably wondering why I'm saying that we need to map keys to indices in the domain 0 to n non-inclusive. The reason for this is that typically priority queues are implemented as heaps, which, under the hood, are actually arrays. So we want to facilitate being able to index into those arrays. This will become apparent shortly. I will say, though, that often, and I mean very often, the keys themselves are already integers in the range 0 to n. So there's no need to actually construct this bidirectional mapping. It's already there implicitly. However, it is handy to be able to support any type of key, such as names or general objects. We can think of an index priority queue as an abstract data type with certain operations we want it to support. Here are about a dozen or so operations we want our index priority queue to support. These are deleting keys, getting the value associated with a key, checking if a key exists in the priority queue, getting the key index with the smallest value, getting the smallest value in the index priority queue, being able to insert and update key value pairs, and finally, the specialized update operations, increase and decrease key, which I'll talk about at the end. For all these operations, you need the key index associated with the particular key that you're dealing with. Throughout these slides, I will be denoting the key index simply as the variable ki to distinguish it from other index values, so keep your eye out for that. An index priority queue can be implemented in several ways. Some ways with really good time complexities using specialized heap structures. However, we're going to cover the binary heap implementation for simplicity. You will notice that the time complexity for all these operations are either constant or logarithmic, which is really good. In a traditional priority queue, the remove and update operations are linear because we are not maintaining a mapping to the position of where our values exist within the heap. Before we dive into the index priority queue per se, I want to spend a few slides giving a refresher on the traditional priority queue data structure, which only supports values, not key value pairs like the index priority queue. Still, both data structures are very similar and most people would consider them the same, although there are key differences in my opinion. Recall that a very common way to represent a binary heap is with an array, since every node is indexed sequentially. If we were to represent the following binary heap as an array, we would get this array of values. If we know the index of node I, we can figure out what its left and right child nodes are by using simple formulas. The left child is 2 times I plus 1, and the right child is 2 times I plus 2, assuming zero-based indices. As an example, what are the children of the node at index 4? Well, we can just plug I into the two formulas I just gave you to obtain the indices 9 and 10. Of course, you can always run the math backwards and figure out what the parent of a given node is. Both of these are especially useful if you're either walking up or down the tree. Whenever you want to insert a new value into the priority queue, you insert the new value at the insertion position at the bottom right of the binary tree. Suppose we want to insert the value 8. This would violate the heap invariant, so we need to bubble up the value until the invariant is met. So swap nodes 5 and 12. The heap invariant is still not satisfied, so swap again. Swap nodes 2 and 5, and now the tree is balanced. Now let's review how removals are done. In a traditional priority queue, to remove items, search for the element you want to remove and then swap it with the last node. Perform the removal and finally bubble up or down the swapped value. For this example, suppose we want to remove the node that has the value 5. We don't know where the node with value 5 is within the priority queue, so we have to search for it. This is one of the major differences between the priority queue and the index priority queue. So start at node 0 and process each node sequentially until a node with a value of 5 is found, if any. So we found a node with a value 5. To actually remove it from the heap, swap it with the rightmost bottom node. Once this is done, remove node 5 from the tree. Now the purple node we swapped into 5's position may not satisfy the heap invariant, so we need to either move it up or down the tree. In this case, since the purple node has the value of 1, which is smaller than its children, and we're dealing with a max heap, we'll want to move the node down. That was a quick recap on just about everything you need to know about a traditional priority queue. Now let's talk about implementing an indexed priority queue with a binary heap. For the following examples, suppose we're dealing with n people with different priorities that we need to serve. Perhaps we're prioritizing people for a queue at a hospital, a waiting line at a restaurant, or who knows what. The main thing is we'll assume that the values can dynamically change and that we always want to serve the person with the lowest priority. To figure out who to serve next, we'll use a min indexed priority queue to sort by lowest value first. The first step, as mentioned before, is to assign each person a unique index value between 0 and n, non-inclusive. These are the key index values in the second column beside each person's name. Then I'm going to give each person an initial value to place inside the index priority queue. These values will be maintained by the index priority queue once inserted. Note that the values can be any comparable value you want, not only integers as shown here. This means we can have strings, objects, or whatever type of data we want. If I was to build a min-indexed priority queue out of the key value pairs I had on the last slide, this is the heap I would get. Remember that unlike the previous example, we're sorting by smallest value first, since we're dealing with a min heap. If I want to access the value for a given key k, first you need to figure out what its key index is, and then do a lookup in the values array maintained by the index priority queue. Here's a good question. What value does the key Bella have in the index priority queue? Well, first, find Bella's key index value, which is 1. Then index into the values array at position 1 to find the corresponding value for the key in the index priority queue. So Bella has a value of 15. Awesome. Now we know how to get the value for a particular key in the index priority queue. But how do we get the index of the node for a particular key? To do that, we'll need to maintain some additional information, namely a position map we can use to tell us the index of a node in the heap for any given key index. For convenience, I will store the position map as an array called PM inside the priority queue. As an example, let's find out which node represents the key Dylan. First, find a key index for Dylan, which happens to be 3. Then look up index 3 in the position map to tell you where Dylan is in the heap. It looks like Dylan is at the node at the index 7, highlighted in orange. Now here's a follow-up question. Where is George in the heap? I'll give you a quick moment to figure that out before I give you the answer. Alright, so with just about every operation, the first step is to find the key index for the key we care about, which is George. Then use the key index to do a lookup inside the position map and find out the node for George, which happens to be node 1. Great. Now we know how to look up the node for a given key, but how do we find the key for a given node? This inverse lookup will prove to be a very useful operation. Say you want to know which key is associated with the root node at index 0. Well, you need to be able to do an inverse lookup to figure that out. To do the inverse lookup from node indices to keys, we'll need to maintain an inverse lookup table. I will denote this lookup table as IM, short for inverse map. Let's see if we can figure out which person is represented in the node at index 2. To do that, simply do a lookup in the inverse map at index 2. This gives us information about which key index is associated with that node. Knowing the key index enables us to retrieve the actual key by doing a lookup in our bidirectional hash table. In this case, the node at position 2 represents the key Anna. Here's a follow-up question to make sure you're still paying attention. Which key is being represented in the node at index position 3? Same as before, find the key index through the inverse map. Then, with the key index, figure out the actual key from the bidirectional hash table. We can then conclude that the node at position 3 represents the key Isaac. What we just covered was how an index priority queue is structured internally, and what all the moving parts are. Now we want to actually do some useful operations with this index priority queue, such as inserting new key value pairs, removing key value pairs based on a key, and also updating the value associated with a key. These are all possible and are actually actually very similar to how you would do it with a regular priority queue. Insertion is nearly the same, except that we have to update the position map PM and the inverse map IM to reflect the movement of the key value pairs. Suppose we want to insert the key Mary with a value of 2 into the priority queue. What we first have to do is assign Mary a unique key index value. Then we're going to insert the new key value pair at the insertion position. Notice that upon insertion, we updated our arrays at index 12 to reflect that the new value was in fact inserted. Currently, the heap invariant is not satisfied since the new node at index 12 has a value less than the one at node 5. To resolve this, we're going to swap the newly inserted value upwards until the heap invariant is satisfied. Swapping nodes, we need to update the position map and the inverse map by swapping the values of the two nodes we're exchanging. The values array does not need to be touched since it gets indexed by the key index value that we get from the map and not the node index per se. It turns out that the heap invariant is still not satisfied, so we need to keep swapping upwards. Let's have a look at some pseudocode for insertions. In this snippet, the user calling this function needs to provide a valid key index, ki, as well as a non-null value they want to insert. The first thing I do is store the value associated with the key inside the values array. Then I update the position map and the inverse map to reflect the fact that a new key value pair has been inserted into the priority queue. Finally, I move the node up the heap until the heap invariant is satisfied. Let's take a closer look at this swim method to see how that happens. Here we are looking at the swim method. You'll notice that it has two supporting functions, swap and less. Swap simply exchanges two nodes based on index, and less determines if node I has a value less than node j. The logic for the swim function is fairly simple. It begins by finding the index of the parent node and walking up the tree. For every iteration, we walk up one layer in the tree. If the index of the current node is not the root node, and the value of the current node is less than the parent node, remember that we're dealing with a min heap, and want small values to be as high up as possible in our heap. To actually issue a node exchange, simply call the swap function and provide the index of the current node and the parent node, and then update the current node and the parent node index values. I also want to talk about swapping and how that actually occurs, because it's slightly different than a traditional priority queue. In this swap method, we're not actually moving around the values in the array. We're only swapping around the index values. Remember that the values array is indexed by the key index, not the node index. So effectively, the values array can remain constant while we update the inverse map and the position map. First, we update the positions of where key index values are found in the index priority queue. Remember what the position map is. It is the position of which node index a given key index is found at. So we can do a straightforward swap by indexing into the inverse map to find the key index values and swap indices I and j. Followed by this, simply update the key index values associated with nodes I and j in the inverse map. To do this, this is just a simple, straightforward exchange. Next up, I want to talk about polling and removing elements from an indexed priority queue. Polling is still a logarithmic operation. However, removing is improved from a linear time complexity to a logarithmic time complexity, since node position lookups are now constant time, but repositioning the nodes after a removal to satisfy the heap invariant is still logarithmic. So let's jump into an example. Suppose we want to poll the root node. This is something we often want to do since it'll give us the key value pair with the lowest value in the heap. The first step is to exchange the root node with the bottom right node. As we do that, remember to swap the index values. Now we can remove the red node from the tree. As we remove the value 2, let's make sure we store the key value pair we're removing so we can return it from our function later. Then clean up the remove node. Finally, restore the heap invariant by moving the swapped purple node down. Since the left and the right child nodes have an equal value of 2, let's default to selecting the left one. Let's do a slightly more involved removal by removing a specific key from the index priority queue. In this example, let's remove the key Laura. The first thing we want to do is get the key index for Laura, which is the key we're working with. So in this case, the key index is equal to 11. Once we know the key index, we can use that information to locate the node within the heap by looking inside the position map. Then swap the node we want to remove. That is the node which contains the key value pair for Laura, and exchange it with the bottom rightmost node. Store the key value pair before the actual removal, clean up the remove node, and finally restore the heap invariant by moving the swapped purple node up or down. We're going to make the purple node move down because it has a large value. Alright, let's look at some pseudocode for removing key value pairs. The code is also very short, only 5 lines of implementation and 3 lines of cleanup. The first thing to do is exchange the position of the node we want to remove and the bottom rightmost node, which is always at the index position SZ, short for size of the heap. Once we've exchanged the nodes, the rightmost node is now in the position where the node we want to remove was, so we need to move it either up or down the heap to satisfy the heap invariant. We don't know which it will be, so we try to move the node up and down, hence sink and swim. Lastly, I just clean up the values associated with the node we want to remove. You can also return the key value pair being removed, but I didn't do that here. Let's take a quick look at the sync method so we understand how that works. To sync a node, we want to select the child with the smallest value and defaulting to the left child if there's a tie. In this next block, I tried to update the smallest child to be the right child. But first, I need to check if the right child node index is within the size of the heap and its value is actually less than the one of the left node. The stopping condition is if we're outside the size of the heap or we cannot sync the current node any further. Lastly, we want to make sure we swap the current node with whatever was the node with the smallest value. Lastly, we want to make sure we swap the current node with whichever was the node with the smallest value. The last core operation we want to do on an index priority queue is key value pair updates. Similar to removals, updates in a min-indexed binary heap also take logarithmic time due to the constant time lookup to find out where the node is and the logarithmic time to adjust where the key value pair should appear in the heap. Suppose we want to update the value of the key Carly to now have a value of 1. Like every operation, find the key index for the key we want to work with. The key index for Carly happens to be 2. Then we can use that key index value to update the values array with the new value. Of course, the heap invariant may not be satisfied, so we need to move the node either up or down until it is. The pseudocode for updating the value of a key is super simple. Simply update the value in the values array and move the node either up or down the heap. It's that easy. Alright, so there was nothing too special about updates, but the part I really wanted to get to was increase and decrease key. In many applications, such as Dijkstra's or Prim's algorithm, it's often useful to be able to update a given key to make its value either always smaller or always larger. In the event that a worse value is given to the index priority queue, it should not be updated. In such situations, it is often useful to define a more restrictive form of update operation called increase key or decrease key respectively, depending on whether you want to increase the value associated with a key, or always try and decrease the value associated with a key. Both of these operations are very simple. They simply consist of doing an if statement before performing an update operation, which either increases or decreases the value associated with the key. So bottom line, these two functions are just convenience methods that wrap a get operation with an if statement to update a value. Today we're going to look at some source code for an indexed priority queue. So just before we get started, make sure you watch my video on the indexed priority queue, where I go over the implementation details and why an indexed priority queue is an important data structure. All the source code for this video can be found on my data structures repository at github.com/WilliamFiset/data structures. The link can be found in the description below. Here we are in the source code for a min-indexed binary heap. This source code is presented in the Java programming language. To get started, notice that our min-indexed binary heap requires that we pass in a type of object which is comparable. This is so we can order our key value pairs within the heap. You'll also notice that I'm extending a min-indexed DSA heap. This is just to be more generic, and all I do in the constructor is simply initialize this heap to have at most 2 children for each node, while a DSA heap supports in general D children. So let's look at the DSA heap implementation where all the fun stuff is happening. So let's just go over, I guess, all the instance variables. So SZ is just the number of elements in the heap, N is a constant representing the maximum number of elements in the heap. D is the degree of each node. So for the binary heap, this number is 2. The 2 arrays, child and parent, track the child and parent indices for each node, so we don't have to compute them dynamically. PM and IM are the position map and the inverse maps, which we're going to use to track the key indices for our keys. And lastly is the values array, which is the array that contains the values associated with certain keys. Note that it's very important to notice that this array is indexed by the key indices and not by the nodes indices per se. So in the constructor, we give a degree and a certain maximum size for our heap. Then we just initialize whatever value for the degree and the maximum size of the heap. Then I initialize all our arrays, and I compute what the child and the parent indices should be. And I also initialize the position map and inverse map to have all -1 values. Then we have a few straightforward methods, such as size is empty, contains. So you'll notice that for contains, we don't pass in the key for our key value pair. Instead, we pass in the key index. And we're going to do this for all our methods. So I just have a few convenience bounds checking methods that you'll see again throughout these videos, such as key has to be in the bounds or throw. So this just makes sure that the key index is valid. And after this check is done, we can check, does that key exist within our heap by looking inside the position map and checking that the value is not equal to -1. Then we have things like peak min key index, which gets the key index for the node at top of the heap, and similarly pole min key index, and also peak min value and pole min value. The reason these are separate is because sometimes we want to just look at the value at the top of the heap but not necessarily remove it. The pole version will actually remove it. Now let's look at insert. So to insert a key value pair, we need to make sure that that key value pair does not already exist in the heap, otherwise we're going to throw an exception. Then I simply validate if the value is not null, and if it is, we throw an exception. Otherwise, we simply update our indices for the position map and the inverse map. Then we assign the values array to have the value we passed in, and then we swim up that node, which we know will be at position size, and we also increment the size variable so that our heap is 1 element larger. Then value of, pretty straightforward, just do a lookup inside the values array. Then delete is slightly more interesting. We make sure the key exists, then we get the index of where that key exists within the heap. We swap the index of the node and the last node in the heap. Then we reposition the new node we swapped into i's position to go either up the heap or down the heap. We capture the value in the position for the key index so that we can return it later. We clean up the node we want to delete, and finally we return that value. Update is also pretty easy. Just make sure that the key exists and the value is not null. Then we get the index for the node, then we capture the old value, update the new value, then move it within the heap, and finally return the old value. So increase and decrease are just short for decrease key and increase key. We're dealing with a min DSA heap here, so make sure you take that into account when looking at the logic. So we make sure the key exists and it's not null. Then if the value is less than the value already in the heap at the values array at the key index, we can update it and also swim it down. Notice that I didn't call the update method here because we know we're going to swim down. In the update method, we sync and we swim, so we do both operations. We don't know which way the node will go, whether it's going to bubble up or bubble down, but in the decrease key method, we do. Same thing for the increase key method, except I switched the order for the last comparator so that the values array is in the first position and the value being passed in is on the right. These are just the sync and the swim methods I talked about in the slides. We can go over quickly. So to sync node I, we get the minimum child of node I. Since we're working with a DSA heap, we need to search all the children of a node, find the one with the least value. This is going to be node J, and then we swap I and J, make sure that I is equal to the value of J, and then we find the minimum child again, and then repeat this until we can't sync the node anymore. Same thing for swim, except that we need to find the parent of node I, which we can just do a lookup in the parents array at index I, swap with the parent, and keep doing this until I is less than the parent. MinChild just looks at all the children of node I and finds the one with a minimum value and returns its index. Also pretty straightforward. Swap, we covered this in the slides. Basically swap the indices and the position map and the inverse map for nodes I and J. Then we have the last function, which simply compares the values for nodes I and J, and other convenience methods. Just because I didn't want to include all the logic of throwing exceptions everywhere, I just kind of wrap them in helper functions. And this is just for tests to make sure that our heap is indeed a min heap. So that's all there is to an indexed DSA heap. I hope there wasn't too much to ingest, and thank you for watching. Please give this video a thumbs up if you learned something, and subscribe for more mathematics and computer science videos. Thank you.